So let us start our discussion on BCD adder. Okay. So basically we are going to discuss about this BCD adder where this particular BCD adder going to have two inputs A and B. Okay. So what is the range of A? So the range of A is from 0 to 9. Okay. And the range of the digit B or the input B can be from 0 to 9. Okay, because these are BCD numbers. And what is the width of A? It is 4 bits, and width of B is also 4 bits. Okay, and the sum which we are getting is of also 4 bits width, and here we can also get one carry out C out. Okay, now so here we can also have one input carry Cn. Okay, which is of 1 bit. Now, so coming to our output sum, so this sum can range from 0 to the maximum value 9 plus 9, 18 plus 1, 19. Okay, so this is the maximum value of our sum, which is from 0 to 19. Okay, so this is our BCD adder. So we should design this BCD adder. Okay, now, when we are performing BCD addition, for example, if we have number 8, which is nothing but 1 0 0 0, and if we have 2, that is 0 0 1 0. If we add this 2, then we are going to get 1 0 1 0. Okay, but this is an invalid BCD number. So this is an invalid BCD code. So if we get any invalid BCD code, what we are going to do? We are going to add +6 to make it as a valid code. So 0 1 1 0. 0 1 1 0 1 1 1 0 1 0 1. So this is our valid BCD code. This is our output C out. Okay, so this is what we are going to design. So if we get a invalid BCD code, we should add +6, or if we get a normal BCD code which is in the range of 0 to 9, we are not going to add +6. So this is our motive. Is it clear? So let us draw the table for this. So I'm going to draw the table for my output. Okay, I'm going to write down my sum. So let me write down in decimal as well as in binary. I'm representing my sum in binary form of representation. Okay, I'm representing my sum in binary form of representation. Okay, so this is 0. My sum can be 0, 1, 2, 3, 4, 5, 6, 7, decimal, and binary form of representation. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So this is the last number which I can go up to. Okay, so 0 is nothing but, and I'm representing it with C out, S3, S2, S1, S0. Okay, so this is nothing but 0, 0, 0, 0. Okay, this is nothing but 0, 0, 0, 0. This is my 3, and coming to my 4, 0, 0, and coming to 5, 0, 6, and 7. Okay, so these are all valid BCD numbers. Okay, so if you represent them in BCD also, you will get the same numbers only. Okay, and coming to my 8, so up to here I will mark one more color. So up to my number, so up to my number 9, so these are all valid. Up to here, these are valid BCD numbers. Okay, so up to here, these are my valid BCD numbers. Okay, now from 10 onwards, these are invalid. Okay, so these are not valid. So let us write them in BCD, the invalid codes. So how to write this 10? How we are going to write this 10? 10 is being written as 0 0 0 1 and 0 0 0 0. Okay, this is your C. and 11 is nothing but 0 0 0 1 0 0 0 1. Okay, 12 is 0 0 0 1 0 0 1 0 0 0 1 0 0 1 1 0 0 0 1 0 1 double 0. I am not considering these 3 bits. I am only having the C. Okay, so whatever you are seeing here, right, the one that is nothing but my C. So when my C is getting, whenever from the invalid codes, I am getting my output C. Okay, can you observe this? Okay, so here I am getting my C. I will write down here C. Sorry, this is my C and this is my S3, S2, S1, S0. Okay, now and coming to my 15, 16, 17. So I will write them in BCD representations. So BCD representation of that is 0 0 0 0 0 1 0 1, and this is 0 0 0 1 0 1 1 0. Yes, so these are your BCD representations. These are your BCD representations. Okay, now, okay, is it clear up to here? And so these are your BCD representations, but your output of your black box which we have drawn here, the output of your black box which you have drawn here, we are not going to get the direct BCD number. We are not going to get the direct BCD numbers. Okay, we are going to get this binary numbers only. Okay, we need to convert this binary into this BCD format. Okay, so let me write from 15 to 19 the binary representations also, 15, 16, 17. Now, so we need to find out the relation now. So we need to find out the relation, and we need to find out the equation from where we can, we need to form some equation. Okay. Now, so up to 9 we don't have any problem. So up to 9 we don't have any problem. Okay. So we're up to here we don't have any problem. Now from 10 to 19 we are having the problem. Okay. So first let us see this last digits from 16, 17, 18, 19. We can clearly see that our C is equal to 1. Yes or no? We can clearly see that C is equal to 1. So first condition what I have got is C is equal to 1. Okay. This is first relation I have got. Next, what we can find out next. So in the numbers from 10, 11, 12, 13, 14, 10, 11, we can see that S3 and S1 are high. Okay, in 10 and 11 we can see that S3 and S1 are high. Am I right or wrong? Yes. So I can write down the second condition as S3 dot S1. Okay, this is one of the equation. And what is the third condition which what I can see? So in this 10, 11, 12, 13, I can see that S2 is either 0 or S1 is high, or either S2 is high and S1 is 0. So I can write this as, and up to this I can see that S3 is high and S2 is high, or either S1 is high. Okay, so I can frame this as S3 into S2 plus S1. That means if S3 is high and S2 and S1 is also high, either one of them are high and or both of them are high. Okay, I can also consider this 14th case also. Okay, and 15th also I can write down the same. Yes, 15th also I can write down the same. So if S3 is high, either S2 is high or either S1 is high, or both are high, S2 S1 are high. Okay, so these are the conditions which I've got. So I can write down, so my invalid conditions, I can frame this as invalid is equal to, if my carry is high, okay, or my S3 is high at the same time, S2 is high at the same time, or S1 is high, or both of them are high, or S3 and S1 are both are high. So this is the condition for my invalid state. So I'm basically what I'm doing from this table, I am framing the invalid condition. Okay, basically I'm framing the invalid condition in the form of equation. That's it. Okay, so my invalid, this will become 1 whenever I'm getting C, or my S3 is high at the same time S1 or S2 is high, or both are high at the same time, and S3 is high and S1 is high. So this is the invalid condition which I'm getting. Yes, is it clear? So you can write it as C plus S3 S2 plus S3 S1 plus S3 S1, which will become C plus S3 S2 plus S3 S1. Okay, which is nothing but C plus S3 if you take common, that is S1 plus S2. So in this particular case, your invalid is equal to 1. So you can cross verify. For example, if you are having a number, let's say your number is 10. So how to represent your 10 in binary form? How to represent your 10 in binary? You are representing it with 1 0 1 0. This is S3, S2, S1, S0. So what is the equation which we have got? C plus S3 into S1 plus S2. So you can substitute here. C is equal to 0, S3 is equal to 1, and S1 is also 1, plus S2 is 0. So you are getting invalid is equal to 1. So it is an invalid code. And let's take a valid code. For example, 9. 9 is nothing but 1001. Okay. So how to take this 1001? So consider this C plus S3 into S1 plus S2. So C is 0, and S3, what is the value of S3? S3 is 1, into what is S1? S1 is 0, and what is S2? S2 is also 0. Okay, that is invalid is equal to you're getting 0. That means it is a valid code. So this is how, with this equation, you are deciding whether the code, the output sum which has been generated is a valid sum or an invalid sum. Yes. Now we need to design a circuit. Okay, so what we are going to do is we are going to have a 4-bit adder. We are going to have a 4-bit adder, and this 4-bit adder is going to have the inputs B3, B2, B1, and B0, and A3, A2, A1, and A0, and it is going to have one input carry Cin. Okay, now so from this we are going to get S3, S2, S1, and S0, and one C out. Now what is the equation which we have got? The equation is C plus S3 into S1 plus S2. Okay, or we can write this as C plus S3 S1 plus S3 S2. So I will write down here. So how to design this? S3 into S2, and yet we can take S3 S2 and S3 S1, S3 S2 and S3 S1. So I will take this S3 and S1, and we should take this C out. So this is our output. Okay, so if this becomes 1, then it is an invalid code. Okay, and this is our sum S2, S3, and S0. And here we are going to have one more adder. Which is taking S0 S1 S0 S1 S2 S3, and let me erase this. Now so here we are taking basically S3, S2, S1, and S0. Okay, and here we are basically taking 0, 0, and this two pins which are, so basically this is A3 A2 A1 A0 and B3 B2 B1 B0. This is also a 4-bit adder. Okay, this is also a 4-bit adder which need two 4-bit inputs. Okay, so the second inputs, the second 4-bit inputs we are providing with S3 S2 S1 S0, and the first 4 bits what we are doing is the MSB and LSB we are making it to 0, and the next 2 bits we are connecting this output. That is what is happening. So if we are getting an invalid code, that is if S3, S2, S1, S0 is, let's say, 1010, that is, it is an invalid code. That means it will become 1 here. So if it is an invalid code, we are going to get 1 here. Okay. That means our S3, S2, S1, S0 will be added with 0, and here we are getting 1, 1, 0. So basically we are adding our output sum with 0, 1, 1, 0. That's it. Okay, and from the output we are going to get the output sum S3 S2 S1 S0, the final output we are going to get. You can mark it as S3 star, S2 star, S1 star, and S0 star. This is our final output, and the carry we can take it from here, C out. So this is how we are going to design a 4-bit BCD adder. So is this clear? So this is how we are going to develop a 4-bit BCD adder. Yes. Now let us try to design a comparator. So let us try to design a comparator. How to design this comparator? Let us see. So basically, a comparator, it is going to compare two inputs. The inputs may be 2 bits, 3 bits, 4 bits, so on. Okay. So this will be your comparator, where you are going to give A and B as your inputs, and it is an n bit comparator which can compare n number of bits. And what are the outputs of your comparator? It can be A less than B, or it can be A equal to B, and it can be A greater than B. Okay, so I am calling this as L, E, and G. That is, if A is less than B, I am calling it as less than, and if A is equal to B, I am calling it as equal to, and if it is A is greater than B, I am calling it as G. Okay. So let us first of all try to understand a 1-bit comparator, 1-bit magnitude comparator. So how to design your simple 1-bit magnitude comparator? You can just take the truth table, okay, A, B, and A less than B, I am calling it as L, that is A less than B, and equal to I am calling it as with E, that is A equal to B, and greater than that is G, A greater than B. So this is my 1-bit magnitude comparator, where these are my inputs 0 0, 0 1, 1 0, 1 1, and your equal to will become 1 here, and your equal to become 1 in these two cases, and 0 0. Now what is this 0 1, which is 1 here, 0 0, and A is greater than B here, 1. Now, so can you tell me the equation of equal to, the Boolean expression for the equal to? So equal to, which is A greater than B, which can be written as, which gate can we use for finding out the equal to operation, whether the two inputs are equal to or not? A XNOR B. We can take a simple XNOR gate, A XNOR B. Now, and what may be the equation of your less than, we can see the minterm A bar B. Okay, so less than, which is nothing but A less than B, which can be written as A bar into B. Okay, this output will become 1 whenever your A is less than B. Okay, and how to write down your greater than, A greater than B, which is nothing but, you can see the minterm here, which is nothing but A B bar, A into B bar. So if you want to see that, you can, from this you can just draw the logic diagram also. Okay, so this is how we are going to design a comparator. Now if we want to design a 2-bit magnitude comparator, how to design this 2-bit magnitude comparator? Again, we can take the truth table for this. Now, in the case of 2-bit magnitude comparator, we will have 2 bits to be compared. That is A1 A0 and B1 B0, where A1 is the MSB and A0 is the LSB of the first number, and B1 is MSB and B0 is the LSB of the second number. For example, if this is 1 1 and this is 1 0, okay, this will A1, this is A0, and this is B1 and this is B0. For this also you can just draw the truth table A1. So I will write down here A1 A0 B1 B0, and less than the operation I'm calling it with a less than b, and greater than, it is nothing but a greater than b and equal to, which is a equal to b. Now for 4 variables we will have total 2 power 4, that is 16. Okay, 0 0, and this is a1 a0 b1 b0 less than a less than b and equal to a equal to b and greater than a greater than b. Okay, and this is 1 1 1. Okay, and followed by 1 0 0 1 1 1. So lastly we will get 1. So you can just fill up the table. Okay, so what will be less than, so this is equal to, here we will get 1, and remaining things we will get as 0. Okay, so this is a less than b. Okay, so it is 1 and remaining things will be 0, and this is also a less than b. So like this we can fill up this table, and after filling this table we can write down the min terms from this. Okay, and this is a small assignment for you. Okay, so please fill up this table. This is simple only, just fill up the table and write down the min terms which are associated with them, and find out the equations of 2-bit magnitude comparator. Okay, how to make a RCA adder which can act as both adder as well as subtractor. So what concept which we can apply here? Exactly. So basically what we can do here is, we know that a minus b can be written as a plus 1's complement of b, or a plus 2's complement of b, whatever you want you can take. Okay, so a minus b can be written as a plus 1's complement of b, or a plus 2's complement of b. Okay, so I'm considering 1's complement of b, and here I'm going to consider a signal which is known as mode. Okay, so if my mode is equal to 0, it will act as a, if my mode is equal to 0, it is going to perform addition, and if my mode is equal to 1, it is going to perform subtraction. Okay, so this is my scene. So what I'm going to do is, I'm going to feed it to an XOR gate. I'm going to take an XOR gates like this, and this XOR gates I'm going to give the signal B. So B0, B1, B2 and B3, and here I'm going to give A3, A2, A1 and A0, and to the other pin I'm going to give mode signal M. Now one of the input of your XOR gate is 1, then what is your output? So if your one of the input of your XOR gate is 1, so what type of gate it is acting as? Buffer or complement? So one of your XOR gate input is 1, so whether it is acting as a buffer or whether it is acting as a NOT gate. So this is your XOR gate A1, A into 1 bar plus A bar into 1, which is nothing but A bar. Okay, so if one of your input of your XOR gate is 1, then it is a NOT gate. So here one of the input of our XOR gate is M. Okay, so if this M is equal to 0, then this XOR gate will act as a buffer, so this B0 will be just passed without any without being complemented. Okay. And if your mode is equal to 1, if your mode is equal to 1, then this b naught will be complemented, because this is nothing but your XOR gate will be acting as your NOT gate. That is, b naught bar will be given, a plus b naught bar will be added, and here a1 plus b1 bar will be given, a2 plus b2 bar, a3 plus b3 bar, that is going to be added. So this is how we are going to design a RCA, which is acting as a subtractor and as well as an adder. Okay, is it clear? Yes. So that's about this particular session. So till now we have completed your adder, subtractor, ripple carry adder, carry look adder, and BCD adders. All this we have completed.